what we need to find here, we got I3 and I1 and incidentally I2, right? Necessarily. And now we want to find the change in the voltage across the capacitor. Now this is where we ran into a lot of trouble understanding what was going on. Okay? I got all kinds of answers about what might be relevant. Okay? You know, everything but the ozone layer, I think. We'd had things that would lead us to find the power through the resistor. Okay? All kinds of stuff, but nothing that came close to addressing how much voltage change across the capacitor. We had good insights, like, okay, you got electric field across the plates. If you know the separation of the plates, you can find the voltage of the capacitor. That's really important to know. So I'm really glad people know it, and I'm really glad you're thinking of whatever you can, okay? Although that isn't going to help a bit because you don't know the dimensions of the capacitor or even the design of the capacitor, okay? And then you know, somebody mentioned the change in the capacitance, and no, we're not going to deal with changing capacitors, okay? You do have adjustable capacitors. That's how you tune, you know, radios that pick up waves, and televisions pick up things, you know, non-digitally over the airwaves. Okay, so there's a lot of good stuff in your thinking, just not the right stuff. At least it wasn't there when we were trying to think through this problem. Now, the fundamental idea is that, what do you mean by a current through a capacitor? How do you get a current through a capacitor? Well, you put a voltage on it, sure. But fundamentally what's happening is charge is being transferred from one plate to the other. Whether a positive charge through some positive charge carrier or a negative charge through a negative charge carrier or a combination of both in two different directions, you have a transfer of charge, okay? And the current is the rate at which charge is being transferred, okay? So I can now say that I3 is the rate of charge transfer across the capacitor. Okay? Meaning that the charge transferred is I3. Well, what is I3? Well, I mean, it is the rate of charge transfer. We said that. It means you multiply I3 by the time interval and you get the amount of charge transferred, right? Now I say the rate, I can say rate with respect to time to be complete, right? Because you want to think of all the words you can while still being concise in what you think and say about a situation, okay? So to be very clear, this is what we do. Okay, so there's the charge transferred, right? Now, voltage is directly proportional to charge Q. So delta VC is directly proportional to delta Q, right? The proportionality constant is C. It's not C, it's 1 over C. Okay? Because voltage is Q over C, charge per volt, right?
That was my mistake.
Yeah, think charge per volt. Because what you want to regard as a big capacitor is one that will take a lot of charge for a little bit of voltage. Okay? And you want to keep that straight. And I just almost wrote it down wrong because I was just writing down symbols, right? I know there's a proportionality constant, so it must be C. Well, no. Okay, it's 1 over C. So the bigger the charge transferred, the bigger the C, the less change that transferred charge has on the voltage. So, we get this, right? And it's not delta T, it's delta Q. Talk about writing down symbols, right? It's proportional to delta Q, and now I've got it proportional to delta T, right? So let me try to make sense out of what I'm trying to say here. Proportionality constant is 1 over C. So, it's this, right?
Yeah.
Right.
And of course that's 1 over C multiplied by I3 delta T. Actually thinking about what I'm writing, and I think it might even be accurate, okay? Does that make sense?
Yes.
And in this case, well, I mean, that's it. Well, that equals then, in the case that I'm solving with my assumptions, that's going to be your 0.3 amps, which is 0.3 coulombs per second, times, let's just do it this way, delta T over C. Okay? And now we got a 0.04 farad capacitor. And of course, when we divide 0.3 by 0.04, we get 7.5. No, we don't. It's 0.75. It's going to be in volts per second. Okay? So now we know the charge in this capacitor is changing at, and it's not 0.75, it's 7.5, it's changing at 7.5 volts per second. Okay? Now, we don't count on that lasting for very long. Matter of fact, we don't count on it lasting for any finite time. Because since the voltage in the capacitor is changing, even if this thing was constant, this voltage across the resistor would be changing as a result of this, right? It's possible this happens to be changing at a rate that compensates for that and keeps the current through the resistor constant, but that's not something that's going to be likely, okay? Unless it's designed to do that. Okay, does that make sense? So, what are the dynamics of this situation now, okay? Well, let me just pose that on another video here.